All right, let us slowly start. And first of all, let me welcome at our AI seminar at Technology Innovation Institute Abu Dhabi, Professor Pietro Michiardi. And Professor Pietro, he received his master's degree in computer science from Politecnica di Torino, and then PhD in computer science from Telecom Paris in Paris. And also he has a habilitation degree, and currently Professor Michiardi is a full professor and head of the data science department at Eurecom. And he has very broad research interests, including scalable machine learning, Bayesian modeling, sample, generative modeling, presentation learning. And today we have a very interesting talk on generative diffusion models. So these models recently impressed many people, not only in the community, but broadly, like in the world. And I think we will have a lot of interesting things on current practice, ideas, and challenges from Pietro. So Pietro, the floor is yours. Please start when you're ready.
Thanks a lot for the introduction and for the kind invitation, and thank everyone for coming to this talk. So today I will introduce the key ideas that we use for a new kind of generative models, which have received increasing attention from the scientific and, as it has been said, from the industrial community. These models borrow their principles from statistical physics, and so they are a bit complicated to understand at first. Nevertheless, they have been successfully applied in many practical applications. So my goal will also be to demystify these models and show how they work in practice. Finally, I'll share some methodological challenges that we are addressing in my group. All right, so here's the menu for today, an overview of my talk. First, I will set up the stage and define the problems we want to solve. I will also give some background on current approaches and the tool we use. It is going also to be useful to provide a broader view by explaining a very important modeling approach, which is called energy-based models. And then I will go to the meat of my talk and present the key ideas of score-based generative models. And finally, I will conclude with 3 research directions that I think you might be interested in. Okay, so let's begin by setting up what are the problems we are interested in. We are interested in 2 goals: generative modeling and density estimation. Okay, I will focus quite a lot on generative modeling and quite little on density estimation, but the methods I'm going to present are really going to work for both problems. All right, so we are given a data set of observation where xi is a potentially high dimensional vector. And for the sake of illustration, I will refer to image data. It's sexier to work with images, so we will stick to image data. So xi will be an image drawn from a data distribution PD. Of course, the data distribution itself is unknown. This is the distribution of all possible images that exist, for example. Then our first problem is that of density estimation. Given a new image that we call ~x, we are interested in knowing whether this image is likely in our data. That is, we are interested in measuring the density or likelihood. I will be a bit sloppy here and use these terms interchangeably, of a never seen before image. Next, our second problem is that of generative modeling. Assuming we somehow learn the data distribution, what we want to do is to be able to generate new data, new images, for example, that are likely to occur, which means, in other words, that are realistic given the data we have. Why are these 2 seemingly abstract problems interesting? Because they unlock several applications, which I will not have time to cover in depth in this talk, but I will show at least some nice pictures as teasers. So just to set the expectation right for this talk, my goal is to focus on the methods rather than on the applications. Nevertheless, if you have questions, please feel free to ask them, interrupt me at any time. Okay, so here's a brief overview of several methods from the literature to address the problems I mentioned. Most of these will look familiar to you and include, for example, variational autoencoders, which are probabilistic versions of the well-known autoencoders that allow data generation. Normalizing flows, which are improvements over variational autoencoders. GANs, which are very famous nowadays and have produced impressive looking pictures, and many, many more. Now, on the right of this slide, you can see a picture that illustrates something that is called a trilemma. When we generate data, we want three properties: high quality, high diversity, and fast generation. Unfortunately, current approaches from the literature do not cover the high quality, high diversity space. And this is why diffusion models have become increasingly important. Also, as a spoiler, you can already imagine that the diffusion models are not fast, and there is a large body of work that is trying to push the barrier and make them faster. Okay, so what I will do next is to briefly name the three ingredients we need to understand to work with score-based diffusion models. We will work quite extensively with the stochastic differential equations. This is where the connections between statistical physics and machine learning appear. I will spend a couple of slides on this topic. I will not go too much into the details, but give you the necessary information to understand what comes next. When we work with SDEs in practice, we have to move from mathematical expressions to computer algorithms that simulate these SDEs. These algorithms are called generally numerical integration methods. Popular algorithms such Euler, Runge-Kutta are in principle very simple to understand and can be implemented in few lines of code. I will not go into the details of these methods, but I assume that you know they exist, and I will mention them when necessary. And finally, we couldn't go without a bit of deep learning as part of our ingredients. And what we will do is to use deep nets as function approximators. However, I will not bother you with the nitty-gritty details of architectures and the hyperparameters of these models. Let's say, at least for now, that someone gives them to us, the architectures and hyperparameters, and we will use them as they are. I will discuss more on this towards the end of my talk. All right, so as anticipated, we needed to spend some time on stochastic differential equations. In our context, SDEs are tools that allow studying the evolution of a stochastic process. So on the slide, you have expression 1, where you have a generic SDE. These kind of objects have been studied extensively in many fields, chemistry, physics, finance, and many engineering fields. As an example, they can be used to study the state of a stochastic dynamical system, such as one composed of particles of food coloring that diffuse in water. I just put an illustrative example here on the slide. Now, the generic SDE in expression 1 has two components. A deterministic component, let me try if I can use my marker. Yes, so you have a deterministic component, which is called the drift, that can be used to model how the variable x varies in time, and a stochastic component that is called diffusion, which models a noisy environment using an infinitesimal Brownian noise. Okay, so the study of these SDEs is unfortunately particularly challenging, because the noise component is almost surely not differentiable, which means that new rules of calculus must be developed. This was done some time ago by two brilliant researchers, Ito and Stratonovich. And even if I will not go into the details of Ito calculus, this is what we use under the hood. Okay, so the complication is that we needed to study the evolution in time of a stochastic process x of t, which induces a time-varying probability density for x. So this is completely different from, first year's university courses where you study deterministic ordinary differential equations, for example, for, I don't know, the harmonic oscillator and so on and so forth, where it's easy to derive analytical solutions to these problems, and everything is deterministic. So to study this kind of SDEs, we use methods that rely on famous Fokker-Planck equations, which allow studying, when it exists, the stationary distribution of such a process by means of computing the partial derivative with respect to time of the density P of x and t. Now, from the practical point of view and in the interest of this talk, what is the take-home message? Given a generic object like the one we saw in equation 1, what we do is to engineer the drift and diffusion terms such that working with SDEs is somehow simpler. So you have an example on the slide in the middle. A simple way of engineering the SDE is to set the drift to be equal to some quantity that you see here. It will become clear later what do I mean by the negative gradient of some function E, and the diffusion to be the identity. Then with Fokker-Planck, it is easy to show that the steady state density, that is when you take the time to infinite, is exactly the exponent of the quantity that we were looking at before. So we can manipulate the SDE to obtain a given stationary distribution. And there are other properties that we will use in my talk. We will use a surprising fact. In principle, we can invert the arrow of time and find out what is the expression, which will be again a stochastic differential equation that allows to go from the cloud of red dot food coloring that you saw in the previous picture back to the single initial drop that generated this diffusion process. Now, we have some background on the tools that we will use throughout my presentation. Let's address the question, which models can we define? And we will begin our journey by going through a very interesting modeling approach. The narrative I will adopt next is to explain the basics, illustrate the limitations, propose new technique, and continue like this until we reach the meat of my presentation. Okay, so we begin with energy-based models, which is a very flexible and general method. Here, the key idea is to associate a real value that we call an energy to each data point we have. The energy is a function, and it is a parametric mapping between the data and a real value. Then we can define a density associated to the energy of a given input. Note that this is a parametric density, which depends on the energy function parameters. Clearly, we are interested in the definition of a valid density, which satisfies the usual constraints that you have here on the slide. It must be positive and unity integral. As you might suspect, our energy function will be a neural network. And essentially what we have done is to transform density estimation to a regression problem. And we will deal with it and train our model and so on and so forth. So this is a very simple modeling approach. And as a consequence, the training is super simple as well. We will use maximum likelihood training and maximize the expected log likelihood, which you can see in expression 4 here on the slide. Now, the problem is that the normalizing constant that we defined before, the normalizing constant Z, is not generally tractable. Indeed, we are discussing about high dimensional data problems, and generally also the number of parameters of our energy mapping are going to be large. As a consequence, computing the integral is too difficult. So, is this normalizing constant really a problem in general? Well, if we were given a pre-trained energy model, then we wouldn't need the normalizing constant. We can compare the density of two data points directly, as shown in expression 5 here on the slides. And this is very useful in many applications, for example, anomaly detection. Now, I'm not going into the details of how you deal with what do you mean by an anomaly, is there a threshold, and so on and so forth. But the basic principle is that I have now a quantity that allows me to compare two data points and say, oh, this has a higher energy and this has a lower energy, and this directly maps to the probability of seeing this data in our original density. Now, for training, instead, it looks like we really need this normalizing constant. When we apply the maximum likelihood procedure, we need to compute the gradient of the expected log likelihood. You have that in expression 6. However, we can play some nice trick. For example, we can just plug in the definition of Z and realize that we can conveniently rewrite the gradient of the log of Z as in expression 7. And as a consequence, we can rewrite our gradient and aim for Monte Carlo techniques to compute an unbiased gradient of the log likelihood, as in expression 8. So here, what we would like is for the energy associated to a data point to be as low as possible, and that of a generated point to be as large as possible. All right, all this looks great. However, we now need a sampling procedure. Indeed, Sampling from the data distribution is easy. This is our training data. And you have this, let me point it out on the slides. You have this in this term here. However, what about sampling from this term here, from p theta? We actually do not have access to this directly, and things are a little bit more complicated. To sample from p theta, we can, for example, use Langevin dynamics, which evolve according to a simplified version of the SDE we've seen some slides ago. So more specifically, if we set the drift to be the negative gradient with respect to x, pay attention, of the energy, and the diffusion matrix to be the identity, then we know that in the infinite time regime, the SDE converges to a stationary distribution that is exactly the density we want to sample from. Now, as a small parenthesis, we have used this interesting fact in all the works that we did on Bayesian sampling, whereby we demonstrate that stochastic gradient descent and more interestingly, Hamiltonian Monte Carlo can be studied through the lenses of SDEs, and we learn very useful properties about these sampling procedures. Now, coming back to my talk, we have our SDE. We can simulate it numerically, for example, using Euler's method, and we can collect samples of p theta. All good? Well, not really, because now we have a costly training procedure involving two nested loops. The outer loop uses SGD to optimize the energy parameters, whereas the inner loop uses SD simulations to sample from p theta. In other words, a naive application of the maximum likelihood approach has something that we call slow mixing times. By changing perspective, we can work toward alternative ways to train these models. In statistics, the score function is the gradient with respect to x of the log likelihood. Now, there's a big debate here because, to be honest, in the statistics books, the score is defined with a gradient with respect to theta, but here we will use a slight abuse of notation and definition, and we call the score function to be the gradient with respect to x of the log likelihood. Okay, so in this case, we can get rid of the non-normalizing constant. You can do easily the computation and see, because z depends on theta and you're computing the gradient with respect to x, z disappears. Okay, so we get rid of this normalizing constant, and some past seminal work shows that the score matching is actually equivalent to density matching, and this is shown in expression 10. As such, we can replace the maximum likelihood objective with something that we call the Fisher divergence, which is shown in expression 11. Now, this is still impractical as we require the knowledge of the gradient of the log of the very density we want to estimate. However, we can rewrite the Fisher divergence as in expression 12 that you see on the bottom of the slide, which solves the problem. You don't have to sample from P of D anymore and work with P of D anymore. Yes, but then we introduce additional computational complexity because we need the trace of a Hessian. Now, some work in the literature address techniques to approximate the computation of the trace of the Hessian, for example, with random projection. But now we really hold all the key ingredients and motivations to move to the meat of my talk, score-based diffusion models. So what I will do next is to illustrate the key ideas of score-based diffusion models, first with sketchy examples, and then with more precise formulations. There you go. The key idea of these models goes as follows. What if we could define a procedure that gradually, according to a well-defined schedule, destroys our data such that it becomes essentially noise? Would it be possible then to follow the reverse of that procedure, such as we could, given an initial noise sample, recover the original data? If we manage to learn the forward and backward dynamics of such processes, then we could simply start from some random sample of noise and generate new data that would be compatible with the original data distribution we used for training. See, for example, the bottom strike we have here. We start from number 9. We are just playing with traditional MNIST here. We start from number 9, gradually add noise to destroy the information, and arrive into a pure noise distribution. Then all we need to do is to learn how to subtract noise and get back to our number 9. Now, more formally, we have that there is a forward path where you start from a data sample, you add carefully some selected Gaussian noise, and arrive at a simple destination, where simple means that it is easy to sample from. Ideally, we reach a Gaussian white noise. One important observation is as follows. We will engineer the forward diffusion process according to its SDE to be affine, because this will dramatically simplify our work. Unfortunately, the reverse path is a bit harder. We start with a sample from a noise distribution and gradually remove noise to arrive at a distribution that is approximately our data distribution. This is the backward process. It's going to be described by its own SDE. And this SDE, unfortunately, is not going to be affine. So what we will do next is to formalize these forward and reverse processes using SDEs and gradually get rid of some complications that arise. My ultimate goal is to show that in practice, this model rely on theoretical sound physics principles to work, but they can be implemented very, very easily. There you go. We replaced our informal statements with some stochastic differential equations. These SDEs develop through time. Now, let's focus first on the top SDE, which models the forward process. This is the same SDE we saw before, but we engineered the drift and diffusion terms to make it easier to manipulate. Even if we don't go into the details, this is an affine SDE, which allows analytic solution to the conditional marginal density. In English, what we can do is to compute the noisy version of the original image we sample from at any time instant analytically. We do not actually need to simulate this SDE because simulation is a costly procedure. Moreover, we can also compute the stationary distribution of the process when it exists. And in this case, the particular SDE I'm showing, it's called a variance preserving SDE. And as a consequence, there exists a stationary distribution. That is, we can compute when the forward process develops for an infinite amount of time, the noise distribution it ends up in. For practical reasons, however, you cannot consider an infinite time diffusion process. You need to define a finite amount of time you diffuse your data. And we call this a diffusion time, capital T in general. This capital T has to be big enough such that the ending distribution can be approximated with the stationary distribution. But in reality, we don't reach the stationary distribution. Next, let's focus on the bottom SDE. Some bright minds derived the reverse time SDE that corresponds to the one on the top. Without going too much into the details, we can see that the bottom expression is very similar to the top one, but with negative sign. There is something more though, the red part, which is our friend, the score that we mentioned before. And that is it. Now we know that what is the SDE to use to start from noise and go back to our image. To be precise, to go from noise to data, we have some problems because since the SDE is not affine anymore, we will have to resort to numerical integration to achieve that. And this is not a super fast process. I guess I saw a message on the chat. Let me just double check. Is the sign of alpha important in the forward SDE? The sign, in this case, no, it's not fundamental. And the reason is that we are actually not really modeling anything in the physical world. So what we do is really to define the drift term to be something convenient. And it has no physical meaning. So we can choose whatever it's convenient to us. In this case, you have just a scaled version of your random variable. Okay, so we cannot go so fast. We have to clarify some of the approximations we are making. So first of all, as I already anticipated, the diffusion times are not going to be infinite. So we will make an error, which is the discrepancy between the ending distribution of a finite horizon forward process versus the noise distribution we will sample from to start the backward process. Moreover, we do not have access to the score. How can we do? Well, we will approximate it by learning a functional mapping, or in other words, by using a neural network. There's much to say about how to design an appropriate neural network here. For example, in state-of-the-art models, they're using super complicated neural networks with skip connections, attention mechanism, and so on and so forth. But the one thing I want to focus on is the presence of a noise level, which is indicated by the time t, which corresponds to how much you diffused your data as an additional input to the score network, because this is very helpful for the score network to understand at which noise level it's operating. Overall, after some math that I am omitting here because we don't have time to develop the derivation of the ELB of the model and so on and so forth, we obtain our training objective for score-based diffusion model, which you see below in the expression 13, and this is called continuous score matching. Notice how we condition on x0, which is the trick we use because we can use actually because our forward SDE is affine. There you go. In green, we replace the true score with the density of our, yes?
Yeah, Pietro, there is a question in the chat. So is the sign of alpha is important in the forward SDE?
Yes, I hoped I already answered it because I saw the message in the chat and I said that the sign is not very important here.
Okay, sorry, I missed, yes.
No problems, no problems. All right, so we arrived at a very intuitive understanding of how the forward process behaves and how the backward process behaves, and how can we approximate the backward process because we don't have access to the true score, and we will use a neural network to approximate the score, and we have parameters theta that we have to learn. So the question is, all these maths seem beautiful and elegant, but how does it work in practice? So what I want to answer are two questions. First, how do we train this model? And second, how do we generate new samples? And the answer is going to be super simple. We will be using denoising autoencoders. Okay, so as I anticipated several times, since we have an affine forward SDE, we can analytically compute the conditional sample at any time instant of the diffusion. And this allows us to use the score matching objective defined before. So in practice, what we do to train our score model is to produce some sort, you can imagine it as an augmented data set. We will sample our images from the training data and produce several versions of such images with a different noise intensity. The noise we inject cannot be arbitrary. It will have to follow some laws, but in principle, this is it. Once we have our augmented data set, we train an autoencoder that learns the noise we are injecting into the image, or to prepare for the next slide, our model will learn which noise to subtract from an image to obtain a less noisy version of it. One additional note on the noise schedule. Some recent work have determined that there are several regimes in diffusion processes. We can discuss them in terms of signal to noise ratio, or we can be a bit more imaginative and say that when the diffusion time t is very large, we are in a regime where learning the score is almost impossible because the signal to noise ratio is practically zero. Instead, when t is moderate, this is where randomness is going to be useful in determining, the semantics of our generated data. And finally, when the diffusion time is very small, this is where we refine our generated data. So what I just said has to be imagined in the context of the backward diffusion process. So when I say the diffusion time is very large, it means that we are at the very beginning of our data generation. When I say the diffusion time is moderate, it means that we are in the first, let's say, the first half of the backward diffusion. And when I say that the diffusion time is small, what I'm saying is that we are very close to the data distribution we are trying to approximate. All right. So since these diffusion processes evolve according to these different regimes, alternative noise schedules, rather than uniform sampling, as you can see in the sketch of the training procedure I have on my slide, you can use alternative schedules. For example, importance sampling that drastically improves the quality of the generated images in the end, or even log normal sampling. These are more details, like I would call them almost implementation details though. Okay, so very quickly, this is how training really works. Our score network is simply a denoising autoencoder, a fancy one, that learns how to recover the original image from a noisy version of it. There are many alternative reparameterization actually. For example, you can learn the noise instead of the image, but we will not bother now. Okay, now the generation of new samples in practice is also straightforward. What we need to do is to simulate the reverse time SDE following a very simple iterative algorithm. So here I have a seemingly algorithm that implements the Euler procedure. We start from noise, we compute the quantities required by the backward process. This also requires the score model that we learn. After one iteration, we will obtain a less noisy version of our noise sample. Then recursively, we re-inject our new distribution as an input and produce a less noisy version of it, and so on and so forth, until we obtain our image. So I tried to do an animation in PDF. Let's see how it goes. I'm not sure it's going to be nice. Okay, so this is how it goes. On the left, we start with noise. We compute all the quantities we need for our backward SDE. We combine them together. We obtain a less noisy version of it, which we re-inject in the input, and so on and so forth, until we get our beautiful 9. All right, so I'm done with the key concept, time to see some results. What can we do with this model? What I will do is to stay in the image domain and present a couple of applications. So here you have a set of samples generated by a recent score-based model. There are even more fancy ones that I didn't cut and paste from these fancy papers. These faces do not exist, but to be honest, they look pretty impressive. And there have been studies comparing the quality measured by a quality metric that is called the feed score of the images generated by diffusion models compared to the past state of the art, which was GANs, and the results are in favor of diffusion models, mainly because of the diversity, not only the quality of the image, but the diversity of the samples that are generated. Next, I'm going to show you a very simple conditional generation example. Here, we slightly modify the sampling objective of the models I introduced before, such that the generated images are conditioned on a given class. It's actually kind of easy to understand the concept in the image domain. You have cipher 10 here, for example, you have all the labels corresponding to the classes of images, and you can inject the label into your objective to generate only images that belong to a class. And this concept has been extended quite a lot in recent diffusion models that have made the news, like Stable Diffusion, DALI, Imagen, and so on and so forth. I will touch a bit on these models later on in my talk. Okay, so another application which is easy to grasp in the image domain is in painting. Here we assume the original image is corrupted, for example, by occlusions or black patches, and the goal is to fill in the gap and generate the missing parts of the image such that they are close to the original data distribution. And again, here there are very clear industrial applications that can benefit from this approach. This does not only apply to the image domain. By the way, I forgot to thank the sponsor of this work, which is Huawei Technologies in Paris, and we are working with the data communication group there. So we are working in the telecommunication domain, and we are using these models in the context of data that does not belong at all to the image domain. Another example is image colorization, which can be used to, for example, restore old images. The idea here is that we have a low dimensional version of an image. Here we are missing 2 channels, and we want to generate a higher dimensional version of it. And this can be useful in applications where we want to store compressed information, for example, and retrieve the original data by complementing it with a generative model. I have a project with a colleague at Eurecom where we work with synthetic DNA to store data, and we are using this kind of generative models to produce codes that are stored instead of the original data. And we exploit the semantics of the recovery, the generation process. So if we store a dog, we will retrieve a dog, but we have no guarantees that is exactly the same dog. So this is another domain, maybe the topic for a different talk. All right. Let me move to the final part of my talk. Let me check the time. Yeah. Where I speak about some of the current challenges in the domain of this diffusion-based generative model. So I will address three main families of work. As it should be clear by now, score-based diffusion models are not cheap. Prior work especially focused on generation speed because we needed to simulate SDEs. And as such, it makes sense to delve into the literature of SDE and find better integrators, or for example, alternative formulations that are faster, like second order SDEs and so on and so forth. Another line of work advocates for the idea of moving to a latent data representation prior to performing diffusion, with the consequence of training and sampling on smaller latent spaces and obvious efficiency gains. What I will do next is to give a one-slide teaser presentation of our work we did in my group to address both training and sampling efficiency by studying diffusion times. Now, an aspect that we did not cover much in this talk concerns the design space of diffusion models, which is really, really complex. It requires specialized architectures for the score network, UNets, and so on and so forth, several tricks to achieve better generative performance. And what I would like to do is to give a one-slide presentation of our work we recently did in the group to lift up diffusion processes in function space. And finally, if times allow, I would like to discuss about multi-modality. So diffusion models have been made famous by using them to generate images based not on labels, but on an input text. However, these models are unidirectional. You can generate an image from a text, but you cannot generate the text from the image. And in a one-slide summary, I will present our current work on general multimodal diffusion models. Okay, so please, this is going to be dense, so bear with me. Overall, what we want to understand here is the role of diffusion times. And to do that, we look at our optimization objective from a slightly different perspective. Here, in the expression on the slide on the top, I'm showing a new decomposition that measures the divergence between the true data distribution, P data, and what we obtain through generation that I called Q. So Q is the density that we obtain at the end of throughout and at the end of the backward process. As you can see, we have two interesting terms. The first one is what we call the gap term, and is a function of the score network that we need to learn and the diffusion time, most importantly. And this measures how good the score network is, or in other words, how hard it is to learn something from the diffusion process as a function of diffusion time. And clearly, the larger the diffusion time, because there is much, much more noise, the harder is the life of the score network. And this, again, is because the denoiser operates in a low SNR regime. The second term, instead, is a divergence between the ending distribution of the forward process, which is finite horizon. It does not go for an infinite amount of time, and the noise distribution we sample from to initialize the backward process. And clearly, the larger is the diffusion time, the smaller is going to be the divergence. In the infinite time regime, this quantity goes to zero. So we begin from noticing that according to this new decomposition, it is possible to find a trade-off between the gap, which would prefer smaller diffusion times, and the KL term, which would prefer larger diffusion times. And as practitioners, we would like smaller diffusion times because it will make training faster and easier, and also sampling. All right, so we can demonstrate, and we did that in our paper, that an optimal diffusion time exists. In the middle of my slide, you can find some simple toy examples where this effect is super clear. These are numerical examples. We also have some proofs in our paper. Now, we know that there is an optimal diffusion time, It is possible also to prove that this optimal diffusion time that strikes the good balance between the gap term and the KL term can be smaller than the usual golden rule of choosing the diffusion time to be, large enough. Now, one may wonder, okay, but wait, how do you find the optimal time? Isn't this costly? And my answer is, we actually do not care. We do not care about the optimal diffusion time. What we do care is that we would like to keep diffusion times as small as possible, because from the training perspective, the gap term is much easier to bring down when the diffusion time is small. And this is, as I said already before, going to be beneficial for sampling. So in the end, the question is, how can we keep the KL term under control? All this discussion is depicted in the figure that you have in the bottom right corner. I hope it is it is visible. I show an ideal diffusion model with perfect score, and this is the yellow line you see in the slides. Let me see if I can help you visualize. So this is the ideal diffusion process. We have a perfect score. We learned a perfect score, and we can sample from the ending distribution, whatever it is. Then in blue, kind of blue, here we have some imperfection, because now we approximate the score, but we pretend we can sample from the ending distribution of our forward process. And finally, here on the bottom, we have the vanilla diffusion process, whereby you sample from a noise distribution that is not the ending distribution of the forward process, and you use an approximate score. And so we can compute the divergences and the approximation errors that we make according to all these models. And our method suggests to use an auxiliary, very simple model to first move from the noise distribution that we have here on the right to the one that is closer in KL terms to the ending distribution of our forward process. And then we proceed with the normal reverse diffusion. Okay, so this has several benefits, especially in terms of costs of training and sampling. If you're interested in more details, you have a link to our paper, and maybe we can engage in some question and answer at the end of my talk. All right, now let's move to another topic, and consider the problems related to current diffusion models. They are super hard to build. The design space is complex. We have many knobs, and it is not evident how to adapt them to different data. However, a recent line of work that we found in the literature suggests that we could treat our data as functions. These are called implicit neural representations, mappings between data domain and data codomain. So in other words, what we are doing is to transform the task of learning and embedding of our data to a regression problem. So for example, for an image, we consider a network, a neural network, whose inputs are the pixel coordinates, I and J of our image matrix, and the outputs are the pixel RGB values at those coordinates. And so we train our network with a regression task, and we use the weights of our network as a representation of our data. Okay, we could have an entire talk on INRs, but my goal here is to pitch our new method to lift the diffusion processes into the infinite dimensional space of function. To achieve this, what we have to do is to define a forward and backward process in general, infinite dimensional functional spaces, which we call functional diffusion processes, or FDPs. Then we needed to prove the existence of such processes, and especially the backward process, which is not trivial. Then, since for practical reasons we cannot work in infinite dimensions, we needed to consider sampled versions of functions. So we use an extension of the sampling theorem to study for which subset of function it is possible to reconstruct them given a countable set of points. And finally, we derive a proper elbow for these monsters and devise practical ways of implementing functional diffusion processes using implicit neural representations. The end result is that we can now generate arbitrary data at arbitrary resolution with similar or better performance than vanilla diffusion models, but we only use super simple MLPs that doesn't require to be a deep learning ninja to be designed. Again, okay, I'm cutting a lot of details. This is just a teaser. I will be happy to engage maybe this time offline because it's super hairy. It took us forever to come up with the proper formulations for this model. And unfortunately, there is some problems with the moderators in AIDRC. And so I still don't have the link, but I will share the link as soon as I have. Do I still have time for one more slide and then conclusions?
Yes, I think so. We started a bit later, so yeah, sure.
All right, okay. All right, so the last part I would like to touch is multimodality. This topic has been studied quite a lot in community that works on variational autoencoders. A lot of prior work focus on how to design, MIMO variational autoencoders, multiple inputs, multiple outputs, where inputs and outputs are what we call modalities. So for example, they can be an image, a text, a radar signal, and so on and so forth. And what they want to do is to perform joint and cross-modal generation. You want to sample from noise and generate 2 or more modalities. For example, in this work, we have been collaborating with Renault, which is a car manufacturer in France. And what we want to do is to sample from noise and generate a camera image and the corresponding LiDAR image. Or more interestingly, at least in the industrial domain, when you are given a modality, for example, a camera image, you want to generate a missing modality, I mean, for example, a sound. And this is very important in applications because you want to make sure that, for example, in a car, if one sensor degrades, it is damaged, or it's broken and doesn't work anymore, you can actually reconstruct with the sensors that are left what is missing. Now, the metrics to judge this kind of system focus on 2 performance indicators. One is coherence and the other is quality. So quality, again, we can use the feed score as for images, for example. And for what concerns coherence, assume, for example, that you want to generate, you're working with 2 data sets. One is MNIST, and the other is SVHN, street home numbers. And what you want to do, for example, when you cross-generate, you have MNIST, that is the available modality, and you want to generate the corresponding SVHN modality. Well, if in MNIST you have number 7, you want to make sure that the image that you generate could be beautiful or not super beautiful, but it has to be number 7. So this is coherence. Now, diffusion processes have been seeing a tremendous interest because they can be guided. You can condition the backward process to generate an image that is compatible with a text, and this is now commonly called a prompt. But these models are unidirectional. You cannot get the text given an image. So what we did is to design a truly multimodal diffusion process which does not require guidance and that can work in any direction. Now, to save computation, we operate directly on latent representations and achieve a super high quality generation and very, very high coherence levels, both in the case of joint and cross-generation cases. And we use a simple technique which somehow resembles to in-painting. And so this is super important work because the current state of the art, I was a reviewer in iClear, and there is a recent paper that got accepted from some people in ETH Zurich. These guys are super good. They do fantastic papers, and they have established the state of the art on multimodal generative models using variational autoencoders. We beat them by 600%, and it's amazing what we can obtain. Okay, so now it's time to conclude. We've gone through a not so quick tour of score-based generative models, which offer super high generation quality. These models allowed us to work on several research challenges, and we are using them in many industrial applications. but these methods are still in their infancy. And one of the main bottlenecks is computational efficiency. As an example, colleagues from the NVIDIA Toronto lab shared information about the cost to produce a single research paper. It was a 2021 NeurIPS paper. And you can see for yourself, I mean, this is astonishing. It's not right. We really need to do better than that. So what we believe is that we see a huge potential in lifting up to functional domains, such models. And we hope to demonstrate with more extensive experiments that indeed such an approach of functional FDPs is interesting. And in our perspective, it is already interesting because we managed to write a paper on that with only 8 GPUs, not 8,000. And we reach the same quality, generation quality as our competitors. So this is already very promising. Yeah, with this, I conclude. Thank you very, very much for your attention.
Yeah, thank you very much, Pietro, on this wonderful talk. It was very, very interesting. And colleagues, please ask questions if there are any. I probably will start from one. We all see that these models, they achieve wonderful results in especially in images, but also in many tasks. And my question is, so do we have anything on the expected performance in like some in theory, like you assume some vector space and you have some objects probably on the manifold which lines, and you make noise and then you try to reconstruct. Why I'm asking, because I know that if you look on manifold learning, then Gaussian noise in high dimension, it's very destructive. So if you have a uniform Gaussian noise and you have a smooth manifold, then you of course can reconstruct, but the rates are pretty bad. So that's why I'm thinking whether we can somehow explain the good performance in practice of all these SDE-based methods.
Yeah, so I've seen in the literature a couple of works, especially from Arnaud Doucet colleagues that work on this kind of data. Now, when it comes to measuring the performance, there are very different ways to do that. And very typically what we do is variational inference. So we define an elbow and we can quantify the performance we obtain by looking at how tight this elbow is. There are also recent papers where it is shown that you can convert the stochastic differential equation into an equivalent ordinary differential equation and compute the likelihood. So you can also measure the likelihood. This is something we prefer to do. Also in our papers, when we report the results, we do not like very much to use the FID score because it's very misleading, the FID score. But everybody uses it, so we have to use it as well. We prefer bit per dimensions, which is, in my opinion, a bit more appropriate as a metric because it is a measure of the likelihood. Now, other performance considerations, I think you mentioned rates of convergence and so on and so forth. This I'm not aware of. It's a bit hairy because you can talk about the convergence of the stochastic process, and so you are studying the diffusion process itself. But I don't think this is what is interesting to you. What is interesting to you is at the end, these SDEs are just tools that we use to achieve a statistical modeling goal. And so rates of convergence in terms of how fast can you learn the parameters of the score network? No, I'm not aware of any works in this direction, especially for the complicated manifold you were mentioning.
Okay, thank you, Pietro. I also should admit that from my personal experience, also FID score is misleading thing, and yeah, we need better measures. Okay, we have quite a few questions in the chat, and the first one is So how can we measure the text relation with the image in the diffusion model? For example, if we add car word to the prompt, what is the effect on images generated? Are the models aware of counting and text added on the images?
Yeah, very, very good questions indeed. So there are different techniques. I would say that there are two mainstream approaches to guide the diffusion process to generate images that are compatible with some text. In stable diffusion, they adopt a process that is a bit more opaque, but very effective. They use the attention mechanism. So they inject an embedding of the text directly into the UNet, the denoising autoencoder at every layer. How can I explain whether this embedding is close to the feature space of the UNet? Honestly, I don't know. Another family of work, which is DALI 2 from OpenAI, and if I'm not wrong, even Imagen from Google, they instead use CLIP. CLIP is another model that has exactly the purpose of finding the similarity between text embeddings and image embeddings. So they have one branch that is treating the text, and this is using transformers, GPT. It produces only encoder. It produces the text embedding, and then they use another kind of transformer, vision transformer, to produce the image embeddings, and then they compute a similarity matrix that ideally the ground truth should be that you have ones only on the diagonal and zeros everywhere else, and they train the model to make sure that this matrix resembles the identity matrix. And so CLIP is a pre-trained model that you can use right now. I mean, you really, with 3 lines of Python code, you can write a text, you can feed an image and get a measure of the distance between the text and the image. Now, how can you make sure the models are aware of more semantic information like counting? If you have seen an announcement on Twitter or whatever, you see generated images of human body with a hand that has 6 fingers or weird artifacts, because they cannot count. These methods are not yet able to do some mathematical operations and counting. So for now, at least to the best of my knowledge, this is an open question. It's more on the application domain. I'm not sure this requires, a fundamental rethinking of the methods themselves, but some nice and difficult engineering tricks to be solved.
Okay, so thank you. The next question is, in multimodal generative models, how can we evaluate the coherence of different modalities? Will there be a unique loss function for each modality?
Right, so there is a metric to measure the coherence between 2 modalities. Let's assume for a moment that we are doing joint generation. So you sample from the latent space of a variational autoencoder, because it's simpler to discuss about variational autoencoder. So you sample from Z, and then you use the decoders to generate. One decoder will generate MNIST, and the other decoder will generate SVHN. So to measure the coherence, what you do is that you take the generated images, you feed them into a pre-trained classifier that spits a label, and you check if the labels correspond. If the label corresponds, +1. If they don't correspond, not +1. And you could keep doing that with many, many samples. You collect enough statistical confidence about how coherent are your data generation process. The same approach applies to cross-generation. Now, when you have, for example, an image and a text, and you want to measure the coherence, what you can do is to use CLIP as a surrogate, because you can measure the distance between the embeddings of what you have generated. So you first generate, you land into the input domain, the real image and the real text, you feed these two modalities into CLIP, and then you get a number that tells you how far or how close they are.
All right, and we have one more question again from Muhammad. Also, if you want to use a pre-trained model of stable diffusion condition or in text-to-image model for another language, should we retrain the whole components, or can we train some components and freeze the others?
Absolutely. So I am aware that people in your group, in your institute, produced the first super large scale language model for the Arabic language. And so you can use that as it is to produce the text embeddings. And then you can feed those text embeddings directly into the model. Now, you will have to use some fine-tuning. And this fine-tuning takes the form of having an image coupled with your Arabic text. And you feed this, but you don't need to train from scratch. You can use a pre-trained model and just fine-tune it.
Yeah, okay, that's very clear. We have another question from Andrei. If approximating gradient of Gaussian kernel density estimator of data distribution with score function leads to such good results, can we further improve diffusion models by starting from a beta estimator such as normalizing flows or other explicit probabilistic models?
Okay, let me parse the question. Yes, I'm going to answer this question with a twist. One of the key components of diffusion models is the idea of perturbing your data with noise. Earlier attempts from the same authors that now are famous because they were the first to produce score-based generative models and so on and so forth, didn't approach the problem with the stochastic differential equation whatsoever. They did what we have in my slides somewhere like, let me find it. So you see the final expression here. So they have been working on that and improving this approach, which already yields not bad results. There are many works from Stefano Hermon and Yang Song from Stanford that attempt at simplifying this part of the computation. There are other works from Pascal Vincent that also find an equivalence between this Fisher divergence and denoising score matching. And so these people have worked on methods that already achieved a good result, but at some point, I think the first one to realize that was Yang Song. They realized that by injecting some noise, it was possible to better guide some sampling processes that were required to work out these expressions. And they started with discrete noise levels, just adding some sample to cover better the manifold in which the data resides. And then the next step was easy to say, you know what, let's consider an infinite number of noise levels. And they went through continuous time derivations. There are other diffusion models that are discrete. They implement a Markov chain. They arrive at the same definition and so on and so forth. Now, the role of noise in its beneficial effects for optimization is already known. I mean, there is something called, it's a weird term, it's called mollification that greatly improves optimization performance. So I've seen some attempts, and someone in my group is working on that as well, to mollify, to introduce some noise in normalizing flows. And so basically, I think that this principle of injecting noise and reap the benefits of injecting noise can be transferred indeed to many other models, in particular normalizing flows. So I think there are very strong connections. However, right now, I cannot point to a published paper that already established all the theory about that. I hope we will be the first.
Okay, great. And questions keep coming. So question from Anis, how can these models be used when we do not have a lot of training data? Can pre-trained models address this problem?
Absolutely, yes. This is basically what kept busy developers in the last 6 months or so. People want to be able to generate an image given a text prompt, but the main character of the image have their own face. And so what is possible to do is with really few shots, few examples of a personal picture to guide the diffusion models to generate data according to the traits of the picture you're feeding in. And this is even faster than fine-tuning because you're not really completely fine-tuning the whole part of the model. And so there are Hugging Face, G-Radio demos about that. It's full of these examples over the internet. And now you even have zero-shot approaches. They are not going to solve the problem that you're mentioning here, but they show the power of these models. So definitely you can, with few examples, you can guide the diffusion models to generate whatever you want. I think the latest kid on the block is called the ControlNet. It just came out, ControlNet, and apparently it's amazing. So you with few shots, you can even just draw a sketch of a cat with whatever drawing abilities you have, and then have the diffusion model to generate a real looking cat the way you drew it.
Okay, wonderful. We had many questions and it means that it was a lot of interest. So thanks, Pietro, again for your very nice talk, and hope to see you some future time or probably some other talk in the future on some new developments. Also, please send the link to this functional paper once it's available, because it's very, very interesting.
What I will do is to send you an email with the link as soon as I have it so that you can share with all the attendees.
Okay, yeah, thanks a lot. Thanks a lot. And yes, we are done for today. So thanks everyone for coming and for questions. Thank you.